Okay, so we are going to talk today about the law of conservation of mechanical energy. Okay? Now, the law of conservation of mechanical energy says that energy cannot be created and it cannot be destroyed. Okay? It also talks a little bit about the work energy theorem when it says energy of a system can be changed if work is done to the system, putting in energy, or work is done by the system, which would represent a loss of energy. Okay? The energy is still not being created, nor is it being destroyed. It's all accounted for. Okay? That's the idea behind the law of conservation of energy. Now, when we do law of conservation of energy problems, we tend to greatly simplify the real world. Okay? Because in the real world, there are things we call non-conservative forces. Okay? These are things that make it look like energy is being destroyed or lost or things like that. So as an example, and this is kind of like the lab we're going to do in a few days, okay, if I made a ramp and I ran a cart down it, when it's at the top of the ramp, what kind of energy does it have? Potential. Okay? When I let it go, it rolls down the ramp, and all that energy turns into what kind of energy? Kinetic. Now, notice I said all of it. Is that what happens in the real world? It isn't. Okay? In the perfect physical world, where there are no non-conservative forces like friction, air resistance, things like that, the amount of energy it had at the top of the ramp and the amount of energy it had at the bottom of the ramp would be exactly equal. Okay? So if whatever situation I did, if I had 200 joules of potential energy at the top of the ramp, I would have 200 joules of kinetic energy at the bottom of the ramp. I would have 200 joules of mechanical energy anywhere along the length of the ramp as potential is turned into kinetic. Right? The potential would go down, the kinetic would go up until I was at the bottom where it would all be kinetic. Everybody kind of follow me there? Okay. In the real world, is that what happens? Okay, so in the real world, that simple ramp conversion, okay, and this is a lab we do in Physics 20, but that simple ramp conversion of energy from potential to kinetic runs at about 40% efficiency. Okay, that means that at the bottom of the ramp, I would have 80 joules of energy left of the 200 I start with. Okay, where does all that energy go?
There's also resistance from the air itself.
Yeah, okay. So there'd be heat, because when there's friction and two things are rubbing together, it makes heat. What else does it make? What other forms of energy?
Sound.
Sound, yeah. You can hear it rolling, right? You can hear the sound of the cart going down the ramp, okay? Friction causes heat, it causes sound, sometimes it even causes light. Okay, sometimes things will glow a little bit as they begin to heat up, okay? Or a spark might fly or something like that. Okay, so all of those represent forms of energy that are no longer in the cart. They're going into the surroundings because it's an open system, okay, which is something we talked about the first day. We're going to be treating everything like it's an isolated system. Something else we talked about the first day, okay, where neither matter nor energy is lost. Okay, so it's all going to be conserved. That is greatly simplifying the real world, but since this is our first foray into the law of conservation of energy, we do it that way because it's kind of easier. All right, everybody with me on that?
Is gravity a non-conservative force?
It is not. Gravity is actually what causes the conversion of potential to kinetic. Right? I work against gravity to set it up there, right? So when it has its potential energy up there, it's equal to the work I do in putting it there. And then when I let it go, gravity pulls it to the bottom of the ramp. So gravity is not a non-conservative force. It's actually the driving force in that system. Okay, so things we need to know. Okay? When energy is transferred to an object, this is work energy theorem, it can cause a change in both kinetic and potential energy simultaneously. We didn't do any problems like that. Okay? We only did problems where it changed either the kinetic or the potential. But in the real world, it can do both. Okay? If I accelerate something up a ramp, I'm changing both its kinetic and its potential energy with the work I'm doing. Okay? So a ball thrown upward has kinetic energy because of its motion. It also has potential energy because of its position above the earth. Okay? And we could add those two numbers together to get our total mechanical energy. So something we need to remember is that mechanical energy equals EK plus EP.
So, you know how kinetic energy is when it's moving? So what happens at the bottom of the ramp when it stops moving?
Well, at the bottom of the ramp, when it stops, it's stopped by something, probably me, in which case I absorb the energy. It does work on me in that case, right? Like I would feel it hit my hand. My hand would probably move a little bit as I stopped the cart. There'd be some sound, things like that. Yeah, that's a good question. Okay, so the sum of both an object's kinetic and potential energy is its total mechanical energy. And that's what we're going to be looking at today, is conservation of mechanical energy. That is all of an object's potential and kinetic energies. Okay? All right, so they've got that written right here. Okay, I don't know why I wrote it, because it was right here, but that's an important formula. Okay, it's also on the back of your periodic table. Okay, but that is how we calculate the total mechanical energy of an object. Okay, so as a simple example of the law of conservation of mechanical energy, okay, let's say I wanted to, just of calculating mechanical energy. Let's say I wanted to calculate the total mechanical energy in this situation. So there's a 0.300 kilogram baseball, okay, so 300 grams, and it's thrown in a straight line through the air, which is physically impossible, but we're going to say that that's happened. Okay, why can't you throw something in a straight line?
It has an arc.
Yeah, why? Because of gravity, exactly. You can't throw something in a straight line. Okay? I know sometimes in sports it looks like something's traveling in a straight line just because it's going really fast, but it's dropping. Okay? Everything drops because of gravity. It arcs to the ground. If you've done any like archery, okay, with a like bow and arrow, okay, if you just aim at a target, you're gonna miss below every single time. If you aim for the bullseye, you're gonna drop below the bullseye because gravity is gonna pull that arrow down as it travels towards it. Okay, that's the same thing with any type of target shooting. Okay, you always have to aim slightly above your target because gravity is going to bring it down. Okay, now in this case we're simplifying things. We're just going to say I threw it, and at this instant it was moving horizontally this fast and was this high above the ground. So we're simplifying things a little bit. Okay, so I want to calculate the total mechanical energy. I know it's 2.5 meters above the ground, and I know it's moving at 20 meters per second. So this number tells me it has potential energy. And this number tells me it has kinetic. Can I calculate how much? Yes. Okay? Because I have the formulas for potential and kinetic energy. We've been using them for over a week already. Okay? So if I want to calculate the total mechanical energy, I use the kinetic energy formula, and I calculate the amount of kinetic energy due to moving at 20 meters per second. And I use the potential energy formula to calculate the amount of energy because it's 2.5 meters above the ground. And then I just add those two together. Okay? Is that pretty straightforward? Right? I'm just plugging in numbers and then adding them. That's a pretty straightforward calculation. All right, so when I do that, I'll take my 1/2 times the mass, 0.3 kilograms, times the speed squared. Okay? And then I'll take the mass, multiply by gravity, multiply by the height, okay, and I get that it has 60 joules of kinetic energy and 7.36 joules of potential energy, which gives me a total of 67.36. They rounded 67.4 joules of total mechanical energy. Okay? Now, as we were saying, if I was to throw that ball, it wouldn't travel straight, it would do this. As it travels through the air and does this, will this number change if this is in the perfect physical world? No, it won't. What will change? Will this number and this number change? They will. Okay, those two numbers are going to change. Because as the object travels through the air, it also falls, which means this number gets smaller and smaller, and this number gets bigger and bigger, because gravity accelerates objects. That's why they can have gravitational potential energy. If they fall, they'll gain speed. Okay? So as this goes along, okay, and the instant it hits the ground, okay, it will have more kinetic energy and no potential energy, but it will still have 67.4 joules of total mechanical energy. That's what the law of conservation of energy says. Okay, everybody all right with that? Okay. All right, I would like you guys to try, let's say just question number 1, or sorry, 8 for right now. Just question number 8 for right now. Okay, let's have a quick look at number 8 here. Right, so it wants us to calculate the total mechanical energy of the clam. Right, so the first thing I want to start out with is that mechanical energy equals the clam's kinetic plus its potential energy. Okay, I know the mass of the clam, I know the height of the clam, and I know the speed of the clam. So I can calculate its potential energy and its kinetic energy. Right, so all I'm going to do here is just put in the formulas. 1/2 mv squared plus mgh. I know all of those numbers, so I can just put them in here. 1/2 times 0.3 kilograms times 8 squared, that would be my speed, plus 0.3 times 9.81 times 30 meters. Okay, when I do that, I should get 97.89 joules of mechanical energy. Okay, everybody all right with that? Okay, now 9 and 10 use this same formula, but they ask you to find either EK or EP instead. Okay, so if I want to manipulate for EK, what do I have to do with EP? Subtract it over to the other side, and vice versa. Okay, so does that make that question like extraordinarily difficult? It does not. Okay, I would like you guys to try 9 and 10. And then when we go over those, I'm going to show you the next step that happens. That's what these two numbers are. So ignore these two numbers. These are the numbers you should come up with if you're doing them the way they're written. Okay, so with question number 9, okay, we have the mass. Okay, so we know the mass is 55 kilograms. Okay, and we know that they leap into the air and attempt to clear the bar. At the top of the leap, the athlete has a total mechanical energy of 3,000 joules. Okay, that's 3.00 times 10 to the 3. So move the decimal 1, 2, 3, that's 3,000. Okay, so their total mechanical energy is 3,000 joules. Okay, they are moving at 8.33 meters per second. So that means they have kinetic energy. Okay, and we are looking for their potential energy. Okay, everybody with me so far? All right. So the formula for mechanical energy is EK plus EP. And I want to find EP. So what do I do with EK?
You subtract it to the other side.
Right, I subtract it over to the other side. Right? So the total minus the kinetic will equal the potential, which is what I'm looking for. Okay, so I'm going to take that 3,000 joules and I'm going to subtract the kinetic, which is 1/2 times 55 times 8.33 squared. Okay, that'll equal my potential energy. Everyone follow what I did there? Okay, I just took the total I subtracted one of the two parts so I could get the other part. Okay? Okay, so that leaves me with 1,091.8 joules worth of potential energy. Okay, here's how I would ask that question if I were asking. I wouldn't ask you for the potential energy. I'd ask you for the height. How would I go about getting that?
Get the potential energy and then alter the formula to make you like try to find the height, and then you just plug in the other numbers.
Right. Okay, I know that this number is EP, which is M times G times H. Do I know what M and G are? I know the mass of the person is 55 kilograms, and I have to assume this is occurring on Earth, where 9.81 is G. Okay, so all I would have to do is divide both sides by M times G. Okay, and that would give me the height. So I have 1,091.8 divided by 55 times 9.81. That would get me the height of the high jumper. Okay, so divide that by 55 times 9.81. 2.02 meters. Okay, that is an impressive high jump. I coached track and field for over 20 years, high school track and field. I can count on one hand the number of times I saw somebody go over 2 meters. Okay, that is an impressive jump. Right, that is, 6'7". Okay, so, yeah, pretty impressive. All right, make sense what we did there? How many people have done number 10? All right, let me give you a couple more minutes on number 10. Okay, and I put in here, just so that you've got it, the 1.88 times 10 to the 3 is 1,880 joules. Okay, so you actually have that number. All right, so I'll give you a few more minutes to finish number 10. Okay, it works very similar, except this one's asking for kinetic energy. Okay, so on number 10, okay, we've got a mass of 2 kilograms, okay, and it's being dropped. So when the hammer's 50 meters above the ground, it has a total mechanical energy of 1,880 joules. Calculate the kinetic energy of the hammer. All right, so I go back to this. Mechanical energy equals kinetic plus potential. And I'm trying to find the kinetic, so I would subtract the potential from both sides. So that'll leave me with the mechanical minus the potential equals the kinetic. Everybody all right with that so far? Now, I'm just going to put in my numbers and formulas here. Okay, we know that this is 1,880, okay, minus our mass, 2 times G, 9.81, times 50, the height. Okay, that'll get us our kinetic energy, which should be 899 joules. Okay, questions on how that one worked? Okay, here's the next thing I'd like you to do. How fast is the hammer going? Okay, you just calculated the hammer's kinetic energy. Tell me how fast the hammer is going. So, the number I just calculated is the kinetic energy. So I know that 899 joules equals 1/2 mv squared. So if I want to find out how fast it's going, I just have to divide both sides by half of m. So 1/2 times 2 and square root that. Okay, that'll give me v. Everyone follow what I did there, right? But that's the formula for kinetic energy. This is how much kinetic energy we had, right? So when we do that, okay, we're going to have the square root of 899, which should be 30, or 29 point something. Okay, everyone all right with that? I think that's what it comes out to. Right, why did I say the square root of 899? Did I forget about this stuff on the bottom? What's half of 2? What's 899 divided by 1? 899, that's why I just said the square root of 899. Okay, so, yeah, so 30 meters per second. Okay, is this making some sense, guys? Uh-oh. Okay, so in the situation there with the archer pulling back the bow, okay, is that a work energy theorem example? It is, right? She exerts a force through a distance, okay, then she lets the arrow go. As soon as it leaves the arrow, it would have kinetic energy. But the higher it goes, that kinetic energy would turn into potential. All right. So the question that kind of comes up after this looks like this. So if she uses an average force of 100 newtons to pull back the bow, and she does that over a half a meter, how much work does she do? $50 joules, force times distance, right? She exerted 100 newtons of force over a half a meter. 100 times 1/2 is 50. Okay, so she does 50 joules worth of work on the bow. There are now 50 joules worth of mechanical energy in the bow arrow system. Okay, right now it's stored in the bow as elastic potential energy. Okay, anytime you have something that is elastic, that is, it can bend but wants to go back to its original shape. When you do work on it, you change its shape. Okay, and then it stores the work you did as elastic potential energy. So with a bow, when you pull the ends of the bow together by drawing the string, okay, you are changing its shape and putting elastic potential energy in. So how much potential energy is stored in the bow right now? 50 joules. Okay, that's where this goes from being a work energy theorem question to a law of conservation of energy question. Once I do the 50 joules worth of work, there are 50 joules of mechanical energy in that system forever. Okay? Or until something happens to the system that makes that change. All right? So, how much kinetic energy will the arrow have the instant it's released from the bow? 50 joules. Again, assuming it's an isolated system. Okay? In reality, when you release a bow, does it make sound? Is it probably some heat? Stuff like that, yeah. And again, the perfect physical world, yes, 50 joules. Okay, what will be the potential energy of the arrow at its highest point? 50 joules, because at its highest point, how fast is it going? Ooh, I'm throwing markers like crazy today. At its highest point, how fast is it going? So it goes up, 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 and then starts to fall back down. How fast is it going right here? 0, right? It's instantaneously stopped, which means it has no what? No kinetic energy. So how much potential energy does it have at its highest point? 50 joules. Okay, that's law of conservation of energy. Right? Once you put energy into the system, that amount of energy will not change unless the system does work on something else. Okay, and that would transfer some of that 50 joules away. This is an isolated system. The bow and the arrow are always just doing their thing. All right. Okay, so the law of conservation of energy states that the total amount of energy in a given situation remains constant. Energy can't be converted from one form to another, but the total amount never changes. Yes. Okay, so the total amount of mechanical energy always remains constant. So we actually write mathematically the law of conservation of energy like this. EI equals EF. Okay, so the initial mechanical energy, and you could put EM in there if you wanted to, okay? The initial mechanical energy equals the final mechanical energy. Now, I can expand that out, and in any problem, I would have to, okay? How do we calculate mechanical energy again? What two things do we add together? The kinetic and the potential. So expanded out, this looks like this. Okay, so EP initial plus EK initial equals EP final plus EK final, right? I'm still saying the mechanical energy at the beginning and the mechanical energy at the end are equal. So, if I had a roller coaster, cart here, cart here, cart here, okay? So it's the same cart, and this is just later. I'm not saying there's 3 carts on the track at the same time, because that would be really dangerous, okay? Because they'd run into each other, yeah. All right, so if I have this situation, okay, I start up here, and let's say I have 4,000 joules of mechanical energy. How much mechanical energy do I have here? 4,000 joules. How much mechanical energy do I have here? 4,000 joules. It doesn't matter where on that track the roller coaster is, its mechanical energy is always the same. Up here, most of that mechanical energy would be in what form? Potential, because it wouldn't be moving very fast up there. Okay? It might be rolling just slightly, so it would have a little bit of kinetic, but mostly potential. If this is the bottom, the lowest point on the track, what kind of energy does it have there mostly? Kinetic, in fact, entirely if it's on the ground. Okay? And what about here? Yeah, about half and half, right? Half would be potential, half would be kinetic. Maybe it's not exactly half, but okay, something like that. Does that make sense to everybody? Okay? But the total, what they add up to, is always 4,000 joules in this case. Okay? So, yes, the amount of potential and the amount of kinetic are always changing, but what they add up to never changes. Okay, that's the idea behind the law of conservation of mechanical energy. Okay, whoop, don't back up. 4 more minutes. So, if I was standing on a cliff, I've lost weight. Very skinny there. And I drop a rock off of the cliff. Okay? What kind of energy does it have the instant I let it go? Just potential, because it's not moving yet. Okay? And when it gets to the bottom of the cliff, the instant it strikes the ground, what kind of energy does it have? Kinetic only. Okay? And all the way down, that potential is turning into kinetic. So could I say that the energy here equals the energy there, if I'm saying mechanical energy? I could. Okay, so this is EI equals EF. Okay, at the top, I would only, so I write this out, say EP initial plus EK initial equals EP final plus EK final, but I would know that at the end, there isn't any of that, and at the beginning, there isn't any of that. So really what I'd be saying is M times G times H initial equaled 1/2 MV final squared. Would everyone be okay with that? Okay, so if I knew how high the cliff was, could I calculate how fast the rock would be moving at the bottom? Should be able to, right? I mean, assume, I don't even need to know the mass of the rock. Okay, because the mass of the rock will mathematically cancel out, because all things fall at 9.81, it doesn't affect its speed. Okay, so if I knew what G was, which I do, okay, I could calculate what F is, what VF is at the bottom, using the law of conservation of energy, which, how we're going to start tomorrow's class. Now you can